I'm also able, do you think, to modify the root with what other operator? Or what other operation? If the square root and division are maneuverable, the square root and multiplication are also maneuverable, which means if I have the square root of 5 over 2 times the square root of 5 over 2, I can rewrite this as the square root of 5 over 2 times 5 over 2. Sorry, no. This should be 2 over 5. Which is just going to be the square root of 10 over 10, which is the square root of 1, and the square root of 1 is 1. Well, technically it's plus or minus 1. So you can think of it that way too, which I didn't explicitly say in class yesterday, but is something that we can do. But the cross simplifying is what I was hoping you would notice. So that was one of the questions out of homework. I'm sorry I didn't answer it last night, but I got the response email too late. So we're going to mark that as red. This person says, could I go over how to solve questions in this section? Use your knowledge of Yes. Yes, we can do that. Questions A through C. Also, could I go over grouping with large and small numbers very slowly? I can also try and do that. Okay. So, we'll do these two first. B and C. Hands, if you did B and C, what were your estimates? Presley, what'd you get as an estimate? You put your hand up having done it.
15.
Sorry?
For B, I got 15.
For B, you got 15. Okay. Anybody else get an estimate for, Shiloh? No, Kyla, sorry. You got 7.4. Those are very different than 15.
I got 7.3. Sorry, I thought it was 10.
You got 7.3. Well, it's close to 7.4. Okay.
I got 7.35.
7.35 is your estimate. Okay. Yeah, Rebecca? 7.75. Okay, so we got lots around 7. So let's take a look at how you did it. Anyone who got an estimate around 7 want to tell us how they did it? Walk us through it. Be brave. Those are all good values. I wouldn't ask you to show me how to do something if you're way out to left field. Aminette, you're avoiding my gaze like crazy. Oh, too bad. I'm coming for you. You have a good estimate. I want to know how you did it.
So what I did was take the square root of the cube root before and cube root after 405.
Okay.
Which is, hold on.
Oh, you mean the perfect cubes?
Yeah.
Yeah, okay, so we found the perfect cubes on either side, which are?
343, which is 7 cubes.
Yeah.
And then 512, which is 8 cubes.
Okay.
And 405 would be in between 7 and 8.
You betcha. Well, the cube root of 405 would be between 7 and 8. Yeah. Yeah.
So the whole number would be 7, and then 512 and 343 are 169 apart.
You betcha.
And 343 and 405 are 62 apart.
You betcha.
And I massaged that to 70 over 200.
Oh, you went to 70 over 200. Interesting. Did anyone who got around 7 would have done the same first couple steps? Different massages. Rebecca, what'd you do?
60 over 180.
You went to 60 over 180. Any other different ones? Yeah. Kyla?
60 over 170.
That's an interesting one because that takes you to 6 over 17. What'd you do then? We had issues because we don't know our 17th fractions. How dare you not know your 17th fractions? Any other fractional massages that we did here? Yeah. Ooh, and then what? Okay, so you did this. You just left a 62 over 170, which takes you to what? Then what did you do? Sorry, say that again. After 31 over 85, what did you do? How'd you get that? No, but how did you get 0.3 from 31 over 85? Okay, one more time? So, oh, you didn't keep simplifying it. Okay, because that only works if it's over 100. Then it becomes a nice decimal. This is not over 100. So we've got to continue massaging this somehow. What you could have done is you could have made this thing a 30 over 90, which would have given you a third. But you can't just take, you got to be careful to not just take the numerator and run with it. 6 over 17, we could massage 6 over 17 to what? 6 over 18, which is the same thing this person did here, which goes down to a third. And then 7 over 200, if I'm not mistaken, takes us down to 35 over 100, which is 0.35. These are all 0.33. So it doesn't actually matter which route you choose. All of these are going to give us very close estimates. We're going to get somewhere in the neighborhood. My estimate was 7. I went this route. Where would I do? I actually went this route here on mine. The 6/17 to the 6/18 to the 1/3. And my estimate ended up being 7.3 repeating. So that's the technique you want to use in there. Comments, questions, concerns about B? Presley, you see where you went? Kind of sideways? Okay. Do you want me to do C, or is doing B enough? We'll do C, okay. Those who did C, those who are asking about C, did you attempt C? You forgot. Did anyone who attempted C unsure of their answer? You know, I'll just do it this way. My estimate was 5.5 repeating. If you are in the neighborhood of 5.5 repeating, you're good. Sorry? 5.5 repeating rounds to 5.6. Yeah, you're good. That is definitely in the neighborhood. You are next door. How'd you do it? Well, it depends on how you did it. Well, then try it. If you get 5.4, I'll take a look. So if you got around 5, if you got in the neighborhood of 5.5, 5.55, 5.6, you're good. Is there anyone who did it who didn't get around that who wants to see how I did it? Okay, cool. I want you to, what'd you get? Oh, then I don't want to show you. I want you to try it before I just, toss you a bone. Because I showed you this one. I showed you B. The procedure is exactly the same. So if you're unsure of C, follow how I just did B. Actually, I didn't do it. Aminat did it. Credit where credit is due. She did it for us. Follow her method for C. Aminat, just so we're clear, where did you get 343 and 512 from?
From the list of
Oh, I see. You were all smart. You went to exactly where we took the list of the perfect cubes on the previous page. Fantastic. There they are. Boom diggity. So if you did not do C, I don't want to show you C. I want you to try C on your own. And if you try it, you show me you try it, you still can't get it, I'll happily do it for you then. But yes, somewhere in the realm of 5.5 repeating is where you want to end up. Okay. Those were basically the questions that was, someone wanted to see, If I flip forward again, someone else wanted to see one of these, estimating square roots of very large and very small numbers with the grouping. I think that's what the other question was. Did this person ask to remain anonymous? Let's look. Oh, that's psychology. That's not this. Oh, this person. Yes. Also going to go over grouping with large and small numbers very slowly, anonymously, please. Okay, so let's go through this very slowly. I will do, from part 4, let's do question number 2, one that I did not assign. Oh, let's take a look at the answers first to make sure we're good on the ones that you did do. Oh, but we already checked those. We're way back. Let's check the work from the homework I gave you. Here's questions 1 through 6 on the bottom. Take a look at what you did there, 1 through 6. I'm sorry I didn't do this already. Yes?
I don't understand how you got, how did you buy it?
Number 5. 5 is a tricky one. So I have 3 root 12 is minus 2 root 12 over root 12. So if I have, this is very similar to, so you've done math with variables before, yes? So if I had 3 x's and 2 x's and I was subtracting them, what would I end up with? 1x. So I have 3 root 12s and 2 root 12s. So if I subtract, I can subtract those just like I would a variable, and I would get root 12. So then I get root 12 over root 12. Whenever I divide by the same thing, it's going to leave me with 1. So that's how I did that. 3 root 12 minus 2 root 12 is 1 root 12. Divided by 1 root 12 is 1. Sneaky question. And then I gave you this. Comments, questions, concerns. Oh, yeah, some of you asked me questions at the end of the day yesterday about questions 7 and 11. Some sneaky stuff going on there. There's 2 things I want to talk about with 7 and 11. With 7 and 11, the important thing to write, there's a few ways you could look at this. Because that we talked about how roots and exponents can be done interchangeably. They show up in the same spot in BEDMAS because they're inverses of each other. So that statement that I just said allows you to do one of 2 things. Either you can choose what order you want to do the squaring or the rooting in here. So the easiest one to do, I don't know how to do the square root of 5. That's I don't know how to do that yet. Maybe we'll learn how to do that today. But I do know how to square 5. 5 squared is 25. And if I square root 25, I get 5. Oh, look, the number that I started with, which is the other hint. Squaring and square rooting, you guys said yesterday, are what kind of operations? Inverse operations. And inverse operations cancel each other out. If I multiplied by 2 and divided by 2, it would be the same as if I had done nothing, correct?
Yeah.
Because they're inverse operations. So squaring and square rooting are the same idea. So when I square something and square root something, I can cancel. Are you dying back there? No, we're good? Okay. When you square and square root something, they cancel, leaving you just with the value that you were going to square and square root, which is how we did these ones. My square and square root cancel, my square and square root cancel, leaving me with 3 plus 2, which is 5. Because they're inverses of each other, they just cancel each other. Cool? Comments, questions, concerns? Which is similar to how I did 12, because there's 2 ways we can do 12. Root 3 times root 3 is the same thing. Because we split up fractions this way, we can do multiplication this way too. That's just going to be the square root of 3 times 3. Well, 3 times 3 is 9, so this is just going to be the square root of 9, which is just 3. Did you do stuff like this in grade 8? No, nothing like this. Does it kind of make sense, though? Some no's. Which part doesn't make sense? Carolyn, you have a question?
Yeah, so everything was just
You have to do with addition and subtraction. You cannot split things up. You can only do the splitting with the multiplication and division. Yeah, so it's like if these things were in the numerator, they have a set of brackets around them. 2 plus 7 is going to be, it's assumed those things are in brackets. 2 plus 7 is 9, so that's just going to be root 9. And then 12 got fuzzy. Well, the other way we can think about 12 is this. If I have root 3 times root 3, how can I rewrite multiplication by itself with a different mathematical operation? I'm taking a number and I'm multiplying it by itself. Squaring. So I've got the square root of 3 squared. Well, squaring and square rooting are inverses of each other, which means they cancel each other out. So the square root and the squared are going to cancel out, leaving me just with the number on the inside, which is 3. So there's a few different ways you can think about a question like 12. Questions? Yes, Rebecca. With what? Oh, here. Well, this one wants you to square things. So this is just, I have the square root of 7, and I want to square the square root of 7. Well, when I square a square root, because they're inverses, squaring and square rooting cancel, leaving me just with the value that was on the inside there. I could have sworn square roots was part of grade 8. One second. Oh, so you hardly did them. Okay. Okay, so does this make sense, but we're uncomfortable with it? Is that kind of where we're at? It makes sense, but we're not super comfortable with it. Okay, so I'll give you more space to practice then. Amina.
In part 5, number 10.
Yes, this one here?
Yeah. Could you go over how you did that?
Sure. So, bed mass. This is, so having a square root over the entire thing is like having, we said that square roots go in the same spot as exponents do because they're inverse operations of each other. So this it would be like the same thing as if I had the square root of 2 squared plus 12, as Carolyn said, if that inside was in brackets. So then I would go inside, I'd do the brackets first. I have an exponent in there, so that's the math I would do in the brackets first. 2 squared is 4. So now I have the square root of 4 plus 12. Because I'm still inside that root, I have to do the math, whatever math remains in there. 4 plus 12 is, so now I want the square root of 16, and the square root of 16 is 4. So that's how I would do a question like 10. Any other questions about any of this? Okay. Flip the page backwards now. If you do have any questions, if you have questions that you're unsure of things, please, 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 please ask. It would be way better for you to ask the question now or to find a brave friend to ask the question for you than for you to email me tonight and then take up a question from today tomorrow. You don't want me to do that. Okay, so estimating is okay. It's not, as awesome as finding out what the exact value of these things might be. Why estimate when there may or may not be techniques for finding out exactly what the answer is, even if we don't use our calculator? So you're flipping back to this first blank page. This is the blank page after using your knowledge. The next page there is blank. This is the page I want you to find. Yes, Danny? Oh, yeah, that blank page right there. Yeah, that one right there. Okay, so you're going to use your knowledge of estimating and then flip one more to the blank page here. And we're going to look at this. Exact values of non-perfect squares. I'm going to turn this light on here. Okay, here we go. Exact values of perfect squares are relatively easy to do. If I have the square root of 16, what is the exact value of the square root of 16? It's 4. Awesome. Well done. How about this? What if I have the square root of 25 over 4? What is the exact value for that? Sorry? 5 over 2. You betcha. I take the square root of the numerator and the square root of the denominator because they're both perfect squares, and I get 5 over 2. Nice. I love it. What about this? Is 45 a perfect square? So this thing is, so the square root of 45 is we want to find the exact value of non-perfect squares. There are a few techniques here. I don't know what this thing is. That is a problem. Up to this point, here's what I've taught you. We can estimate using the techniques that I have shown you in class already. We could find the perfect square below. We could find the perfect square above. We shove it in the middle. We find the fraction that represents the distance between those two perfect squares, and then the first perfect square and our value. Then we massage the fraction to make it close to something we can simplify and blah, 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 blah. What else can we do based on what I've shown you in class already? There's one other maybe technique you could use that you're not allowed to use yet, but I've technically shown you how to do. A calculator, yes. So the estimate gets us close. The calculator. Is the calculator an exact answer? Someone said no. Who said no? Jay, why you say no? No, you didn't. Who said no? Jay, commit. If I call on you, it means I like what you said. Who said it? Okay, why are calculators not great? Calculators get us much closer, but do they get exactly there? Who said no? Gavin? Gavin, why don't they get us exactly there? Kyla? Not necessarily. Any other thoughts? Yeah, Danny?
It really depends on the person that's doing it and what they're plugging into it.
Yes, but yes and no. I mean, I'm assuming I'm hoping at this point you could all find the square root of 45 on your calculator. What's the problem with the calculator though? It only goes a certain number of decimal places, and then it'll round it for you, or you round it, because it's an infinitely long decimal. Okay? The calculator is limited by screen size. Oh, I assure you it is. Yes, but they too will stop. screen size and computing power. Also with the calculator, we round. A rounded value is not an exact value. So then what the heck? We want to find a way to find the exact value of the square root of 45. To find the exact value we are going to do something called, factorize. Dot, dot, dot. Hands up if you know what it means to factorize a value. Hands up if you know what a factor is. Few hands, I like it. Who wants to try and explain what a factor is? Okay, I'll say it this way. Hands up if you know what a factor is but didn't want to admit it because you thought I was going to call on you to explain it. I appreciate the honesty. Who is willing to explain what a factor is? Presley.
I'll try. A factor is a number that you can. A factor of 45 would be 9 because you multiply it by 5 to get 45.
Okay, here we go. So 45 can be broken up into its factors. Now, one set of factors is 9 and 5, as Presley has already given to us. These guys here are factors of 45 because they multiply together to give you 45. So what we're going to do is this. We will factor to find perfect square factors. That's our goal. So, 45 can be broken up into 9 times 5. Is 9 or 5 a perfect square? 9 is. We like this. So what this means, because we found a perfect square, we can stop with our factors. And we can jump straight to this. Because 45 is made up of 9 times 5, the square root of 45 is going to be made up into the square root of 9 times the square root of 5. Are we cool with my reasoning here? Anyone taking issue with my logic? Because 45 is 9 times 5, the square root of 45 is the square root of 9 times the square root of 45.
Right. That makes sense.
We'll get there. We're stopping here because 9 is a perfect square.
What if it wasn't?
We'll get there.
Okay.
So what is the square root of 9? 3. So I can rewrite, instead of having the square root of 9 times the square root of 5, I can make the square root of 9 what its value is. It's just 3. So then I can say that this thing is actually 3 root 5.
Wait, what? What did you say?
The square root of 9 is 3.
Yeah.
So if I actually just do this section of the math, I'm going to get 3 times root 5,
Oh, okay. You're like,
which in math, the language we use to describe this is 3 root 5. We don't say 3 times root 5, we say 3 root 5.
okay, that's what it looks like. Yeah.
Yeah. Does anyone need to be convinced of any of the steps I've made here? Hands up if you're like, yeah, it makes sense, but I'm uncomfortable. Okay? That's the sweet spot. That's where I'm going to try and hang you all semester. I want you to be like, yes, this makes sense, but it makes me feel like worms are crawling inside me. Because that's where you learn. That's where it means I'm teaching you things that you're getting, but you're still being forced to grow as a mathematician. So, Danny asks a really good question. What if the numbers we pick aren't perfect squares? That's a phenomenal question. Danny, I'm glad you asked it. Let's do it again. Same numbers. Well, same starting number. We're going to start with 45. What are two more factors of 45? And I want you to pick them is such that neither of them are perfect squares. A 1 and 45 is not useful. True, but not useful. I heard something over here. 15 and 3. When both of you make eye contact with me, I can't tell which mouth is moving behind the mask. Okay, 15 and 3. Are either of those perfect squares? No. So we're going to keep going. And we're going to make what's called a factor tree. Have we done this before?
No, not again.
We're doing it again. It's not dumb, it's useful. Okay, so how does a factor tree work? Yes, now we do the factors of 15. So we go to the end of the branches and I say, okay, well, are there factors of 3? No, because 3 is? Oh, because 3 is prime. I love that you guys know that. The square root of 15, sorry, no, not square root of 15. What are the factors of 15? 3 and 5. I'm actually going to write it as 5 and 3. For reasons that are going to make a little bit more sense here in a sec. Can I take this any further? Why not? I'm not going to break it into decimals. Can I take this any further with whole factors? Why? Because they're primes. Yes. This thing right here is called a prime factorization. And some of you have definitely seen this before. You don't like it, but here it is. And what that means is 45 is equal to all of the ends of the branches multiplied together. 5 times 3 times 3. Yes? We cool with this? So the square root of 45 is going to be equal to the square root of 5 times the square root of 3 times the square root of 3. Which is very similar to what we've got before. Square root of 3 times the square root of 3, well, that's just the square root of 3 squared. And if I square a square root, what happens to it? Cancels out. So this piece can be written as root 3 squared. Those just cancel, leaving us with the whole number 3 times whatever we have left, in this case root 5. Which I sure hope is the same as what we came up with before. So the exact value of the square root of 45 is 3 root 5. And that's it. It's done. Danny. This is it. This is where it ends.
But it'd be different. The answer would be different if you did it the other way.
What other way? I'm going to do another example here. If you're really quite bothered by what's going on here, there's a shortcut that I want to show you.
This is square rooted.
Yes, this is exact values of non-perfect square roots.
Because we did non-perfect square roots before.
We estimated them.
We estimated them. But this is,
Before we had, so yes, Danny's bringing up is, before those were estimates. Those were, can I get close to the value that my calculator will give me? Yeah, sure. But now what we're doing is there is no rounding, there is no estimating. This value is perfect. 3 root 5. Of course, if I shove this thing into my calculator, it's going to give me this ugly monstrous decimal. But this value is exact, as we've written it, 3 root 5. And there are times where you will have to do mathematics with results like this. And if we were to do more calculations with a calculator value, because the calculator rounds, because you round, because we're limited in the decimals that we can go to, our new calculation is going to be off because we're using a value that's not exact. By using this technique, factorizing to find an exact value, we can take this value, whether you like it or not is irrelevant, we can take this value and do more things with it, knowing that that final answer is still exact because my values along the way are exact. It's like using 1/3 as a fraction versus 0.33. 0.33 is not an exact value. 1/3 is the exact value. 0.33 is a rounded approximation. So this technique that I'm showing you here is actually the most useful thing I've taught you so far, that you're actually going to move forward and use in your mathematical career from here on. Danny.
So if we estimated the square root of 45 using the technique that you showed us before,
Yep.
we'd end up with, like, can we do that and compare the answers? Because I don't feel like they'd be at all similar, but they're the same. But
Well, they're not going to look similar.
they're pretty close though. Like
They're not going to look even remotely similar.
No.
Because if we estimated the square root of 45, see if you can follow this. I'll just do it in my head real quick.
Okay.
So it's going to be between 36 and 49. So the estimate is going to be between 6 and 7.
Yeah.
The distance from 36 to 49 is 13.
Yeah.
The difference between 36 and 45 is 9. So it's going to be 6 and 9 over 13, which is going to make 6 and 9 over 12, which is going to be 6 and 3 over 4, reducing that fraction, which is going to give me 6.75.
Yeah.
It looks nothing like 3 root 5.
No.
But if I took 3 root 5 and I shoved it into my calculator, and I just write it as it's written here, I'm going to have, turn it on. There you go. 3 square root 5. And on the Casios, I'm actually going to have to push this SD button, 6.708203932, which is the same thing as if I'd done the square root of 45. But this is a value, this is a rounded value, or this value ends. That is an exact value. And these Casios can actually give you both, which is sneaky. Yeah? Because I specified estimate, no. Oh, yeah. But the instructions would say either simplify or find an exact value. You have to do whatever the question's asking you to do. Let's do another one. And I'm going to show you a shortcut. I hope you have room. I have a little bit of room, so I'm going to do this last one in this section right here. Another example. Right here. Okay. You guys still have room? Yeah, you do. Okay, good. I want this. The exact value of the square root of 80. Okay, here we go. So, to find the exact value of the square root of 80, I'm going to use the same kinds of techniques that we've used here, except I'm going to introduce to you a shortcut part of the way through. Let's do the factor tree for 80. Unfortunately, you still have to do that. Except this time, I don't care about finding perfect squares. I'm just going to drill down all the way to the bottom. I want the prime factorization. Just go nuts. What times what is 80? 40 and 2. Ugh. Okay. What times what is 40? 20 and 2. Okay, what times what is 20? Oh boy. What times what is 10? And do we have a prime factorization now? Yeah. 5 and 2 are all primes, and all I've got are 5s and 2s. Thank you for giving me the worst possible combination of numbers. I love it. But it still works. It actually works quite well for us. If you look back at what we did here, what do you notice? When I was finding the exact value of the square root of 45, where I had a pair of factors, these guys, because it ended up being the square root of 3 squared, those squareds cancel, and what they do is they end up giving us just one of that value multiplied out front, yes? So rather than writing it out like this every time, if you recognize this to be true, what you can do is jump straight to this. The square root of 80, and if we look at the factor tree, is going to be equal to, if we look at the factor tree, for pairs of common factors, these two 2's, we're going to do the same thing here that we did with these root 3's. If I actually write it all out, it'll give me a root 2 times a root 2, which is a root 2 squared. Or I can recognize where we're going and see that, well, this pair of 2's is going to pop out as a 2 out front. This pair of 2's is going to pop out as another 2 out front. Those are going to be multiplied together. And this 5, that's a poor sucker with no partner, is going to stay inside as a root 5. And then this thing is going to give me 2 times 2, which is 4 root 5. I had a math teacher in high school who called this thing jailbreaking, because you need a buddy to get out of prison. See, the 2's have a buddy, so one gets out. The 2's have a buddy, so one gets out. 5's a sucker all alone, stays in prison. Is how my math teacher explained it to me in high school. If you like that analogy, it's a neat little way of thinking about it. Kyla, you have a question?
What if you have an unequal amount of primes?
What do you mean?
Instead of 4 2's or 3.
Oh, that's a great question. Maybe we should flip the page and do another one. Oh no, you say that like that's not where I wasn't going to go anyway. Kyla asked a really good question. What happens if I have a not a nice value? So what we're going to do is here, we're going to do the square root. Another example. I want to find the square root, the exact value for the square root of 160. How are 160 and the previous question related to each other? It's double, so there's going to be another factor of 2. Who said it? Was that you, Kyla? Did you say 2? You're right. Let's do the factor tree for 160. I'll just do it real fast for us here. It's 80 and 2, and then 40 and 2, and then 20 and 2, then 10 and 2, then 5 and 2. I write big, so my factor tree is large. We're going to use the shortcut. 2 2's going to jailbreak out, giving us 1 2 outside. This pair of 2's is going to break out, giving us another multiple of 2 on the outside. Does this 2 have a buddy? Does this 5 have a buddy? No, so they stay in the root, multiplied together, because they are they're also factors of 160. So what I'm going to get here is 2 times 2 is, and 5 times 2 is, so my final answer is 4 root 10. It's a great question, Kyle. I'm glad you asked it. Comments, questions, concerns about what we've just done? Okay, well, if you don't have a question for me, then I have a question for you. What if we, instead of having square roots, what if we increase the root? Can we do something similar with cube roots, or fourth roots, or fifth roots? You bet we can. It's a good thing we're gonna. Let's go. Oh no! Here we go. What about cube roots? How about fourth roots? Bigger? Question mark, question mark, question mark. You think you're good, but you're not. Okay, here we go. I'll give us a nice easy one. I want to find the exact value for the cube root of 32. Now, before I go any further, does anyone have any ideas as to how this might be related to what has come before? Thoughts on where we might be going? You betcha. You betcha. Here we go. She's absolutely right. So when we have a cube root, because it was been given to you, I'll give it to you now. We need 3 matching factors. Because cubing or cube rooting something is looking for the number that, when cubed, i.e. multiplied by itself 3 times, gives us our value that we're starting with. So, cube root 32, exact value. Here we go. 32. What's the factor tree for 32? 8 and 4. Can't break either of those up? Or first of all, let's just keep going. Let's go all the way to the prime factorization. Can I break up 8 and 4? Someone said yes, someone said no. I can break up 8 and 2. What? 4 and 2, and I can break up 4 into 2 and 2. This 4 can also be broken up into 2 and 2. Now, because a cube is looking for the thing that multiplies itself 3 times, I need a group of 3 of the same factor. Do I have that? Yes, these 3 right here. So those 3 2's are going to pop up, giving us 1 2. And these 2 2's don't have a third matching buddy, so they're going to stay inside the cube root this time, and 2 times 2 is 4. So the exact value for the cube root of 32 is 2 cube root 4. You can think, if I take my analogy from before and I just crank it up a little bit, where my teacher called it jailbreaking, you're breaking out of prison. If a square root is a prison, then a cube root is a higher security prison, so you need more buddies to break out. The higher the security, the more people in your team you need. A cubed prison means you need 3. A fourth prison means you need 4 matching factors, and etc., etc., etc. Oh, matching-ing. No, not that. Matching factors. Comments, questions, concerns? You want to give it a shot? Well, you have no choice. You must. So here's what we're going to do. And you've got lots of time to work on this. 5, 10, 15, 20 minutes. What I want you to do is this. Flip And then flip again, because I already assigned this to you. Oh, snap. Look what we have. What is this? Okay, so before I assign anything, let me explain to you what you do. And I love it when people say, what's this? I immediately think of Nightmare Before Christmas. What's this? What's this? I don't actually know the rest of the song. I just know that a tall skeleton starts that way. And it's fantastic. It's applicable to so many things. So, this first section, the instructions say, okay guys, the instructions here say simplify. What I mean by simplify is exact value. Give me the exact value of that root. If you flip the page and then look over here, you will see that I have provided you with the answers. Look at me being all benevolent. You can check your own work this time. I'm not going to check your work. Why would you just write them down? If you just wrote them, I don't check your work. Writing them down, just the answer down, doesn't actually do anything. If that's what you're going to do, then just don't do the homework. But I guarantee you, I don't check homework, but I guarantee you, when I give you a test or a quiz, if you haven't practiced this at least a little bit, I'm going to get you. And then you're going to get got. And then you're going to have to answer to someone bigger than me, i.e. more important in your life perhaps, because after the semester's done, you may never see me again. But you got to live with a certain set of people forever. They might care. Yeah, those people. If you flip the page again, look what I have given unto you. Oh, look, they're cubes. If you look on the next page, oh, look, there's fourths. If you flip the page again, oh look, there's fifths. I'm a terrible person. If you flip the page again, oh look, there's answers. And if you flip the page again, you'll see that it ends with the next lesson, so we're not going to go any further than that. What I want you to do, no, I'm not assigning all. All is 40 questions. What I want you to do, and as actually, teachers who assign all actually do a lot more work for themselves. Because some students come back and say, oh, but I want more practice. And then I have to make you more practice. So what I'm going to do is I'm going to assign half the questions. But I still want you to go through the entire thing because they get harder as you go. So what I'm going to do is I'm going to assign odds. You don't want odds? You're complaining about odds? Flip back then to where I gave you this. On this one, let's be crazy and do evens. So with exact values of square roots, you're doing the evens. For the exact values of higher roots, you're doing odds. You got 15 minutes now because it took me 5 minutes to explain that. On your market set giver.
This is odds, the one with
The higher roots.
7 to 4. That's odds.
Which one are you looking at?
7 to 4.
No, so like you've got the square roots, 1 to 20. The exact value. So Danny, the exact value of square roots, 1 to 20, evens.
This is 1 to 20.
Yeah, 1 to 20 evens. And then you flip again, and it's higher roots. There's cube roots, fourth roots, fifth roots. That one's odds. The square roots are evens. The higher roots, like the cubes, the fourths, the fifths, those are odds. Squares are evens, cubes are odds, and you've got the answers available to you. I'll take up any questions you may have tomorrow, and I'll come float around and help any of you now. Give it a shot. Exact values. The estimating's gone. No calculator. Exact values. Giver.